No? So you can find your graph. You had to change your window to drop this down. But visualize your window. If you don't see a turn, push this down. That's your Y min. Just double your Y min, and you'll get to see a turn. Your maxes and your mins, these are both relative because it's all real numbers for your domain and your range. So your absolutes don't exist. Make sure you give me 3 decimal places. I put this one in case you wanted to flip it to a fraction, hoping that maybe someday you'll like fractions. You can flip that into a fraction as well. Relative min, that relative max, that one came out good. If it's helpful if you label these. So you can label this point A, you can label this point B, and it's easier for me when you label. Domain and range we said was real numbers. Your intercepts, remember, even though you can spot them, you may be able to spot them, and sometimes the y is a 0, 0, like the x is a 0, 0, but you still have to solve everything algebraically. You can confirm it on your calculator. So you set this to 0. Were you guys able to group this to factor? This had 4 terms. Were you grouping? Group it and factor. So you've actually got 3 roots here. You have 3 of these. A nice way to do this, and if you put this in your calculator, it's going to say 1.732 if you look it up. But a nice way to check this is once you graph, do this. Second calc, 1 for value, put in x at radical 3, and it will come back and say your y is 0. That's a good way to check, because if you did a min and a max and you did the zeros on this, everything comes out decimals, nothing comes out radicals. It would say 1.732, blah, blah, blah. 1.732 is your radical 3. But an easier way to check is to put it in as a value, the exact value, and it will come back and return that. Okay, increasing, decreasing, good. And when we substituted in your negative x, this was neither. And we can tell right away, there's no reflection over the y-axis, and there's no reflection through the origin. You tell me if there's any questions. No? Looking good? Okay, your review, so you have to speak up and tell me. Okay, piecewise. Let's hit piecewise. Piecewise says I have more than one function to make this entire thing happen. I've got this in pieces. Now your pieces go by your domains. So I always tell you label 1 and 2. Look for your domain. This domain says get me from 0, not don't count 0, to infinity. So table 1, start at 0 and give me a couple of that domain. Table 2 says 0 include and all the negative numbers. So in table 2, give me some negatives and it's 0. Give me a solid here, give me an open guy here. This still gives you a function if one is open and one is closed. That's why we call this a piecewise function. It's still a function. Now all you have to do is put this in your y equals, just this piece, and go to your table and pull out your y values. When you do this, notice that this guy is a parabola. It is a parabola that goes like this. You want this piece. So this piece over here has to have a curve to it. It can't be a straight line. It's a part of a parabola. This guy here, put this in your y equals now. Pull out this part of your table, and you also notice that this guy was a parabola. And you only want that piece right there. And therefore you notice it's going to have to also have a curve, not a straight line. And we're basically sketching the points with the opens and the closed circles. They're the most important ones. This does pass a vertical line test because one is open, one's closed. And we just sketch. Good? All right. The second one, same thing. If you struggle, use a number line for your domain. Start your domain at 1, go to infinity. So start it at 1, open circle, and give me a couple that run to that side of it. This guy, table 2, is going from here to the negatives. So give me a couple of negatives, end it at 1, close circle. And again, put this in your y equals, and fill in your y values. Now, it's also helpful to remember that was a quadratic. So the first one's a quadratic, it's got a curve to it. And the second one is a cubing function. You're also catching it on the cube before it turns. So it's kind of helpful to see where they're going as well. And remember, one is open, one is closed. Just a sketch. Just a sketch. It's kind of nice to catch the 0, 0 here, so that it's not like too wide. That kind of gives you like, there's your intercepts. We usually use intercepts to guide how wide your graphs are going to be. It's just like eyeball points, because that's the point that you really tend to notice the most, is the 0, 0s. This one has 3 sets, 3 pieces to make this. Your first piece is going from -1 and your negatives. So give me a couple of, again, label them. Give me a couple of negatives, ended at -1, close circles. Your next one's going from -1 to 3. They're both open. Give me some values in there. No decimals, just your whole numbers. They're both open. Your last one's going from 3 to infinity. See how it used all your real numbers eventually? And so give me 3, 4, 5 is fine. Your first one is a line y equals x, right? So all your y values will be the same as your x. And you'll get, normally this line goes here through both of these quadrants. You only want it to stop right there, and you want that to be a solid circle. The next one starts here. This is a constant line, y equals 2. This line goes like this. You only want the section from here to here. So we draw that piece of it. The next one's part of a parabola. You want that parabola from 3 on out. And you draw your 3 on out. Make sense, Kyla? Mm-hmm. It's a piecewise, piece at a time. It should still be a function. It has to pass the vertical line test on anything that you do. One's going to be open, one's going to be closed. I wouldn't be able to give you one that has 2 closed, because then we wouldn't call this a piecewise function. We call it a piecewise relation. Okay? Stop me if you have any questions. How'd your sketches come out? So try it. Do they look like that? Yeah, kind of weird, right? Sometimes you'll get to do more of these and we'll see them turn as well. Just to give you a flavor for this. Your domain, what's happening, a good way to start is to start with your domain. Your domain was solid at the 4 and the -4. Your domain is this way and this way. So you know your graphs are not happening in the middle, right? This is where your domain is. Your range is from here on up. So you know your graph is not happening down here. Your absolute minimums are those points, those intercepts. That's where it's going to start, and it's going to decrease from -infinity down to the x value of -4. It's a decrease. And then it's an increase from 4 to infinity. It's even, have symmetry over the y-axis, right? We can tell right here, these are spaced apart equally. Okay? Now, could you make your decrease be a solid line? Absolutely. It can be a solid line. Nobody said it had to be a curved line. We don't know if this is an absolute value or a parabola. So yours can absolutely have solid lines here, straight lines. How many of you did okay with the difference quotient? Okay, let's work the difference quotient out. I got a spare. No spare. Right here. Okay. If someone could just read me that. 4 squared. Okay, so we're going to do your difference quotient. Your goal is to factor eventually and eliminate that h. Easiest way to do this, guys, this is f at x. Make this guy x. If I gave you f at 3, what would you do with the 3? If I said f at 3, just a function notation, what would you do to the 3? Oh, you'd plug it in for x, right? So all I'm saying is f at x plus h. So now x plus h goes in wherever you see x. It's no different. So rewrite this. 4x plus h squared minus, now this is a minus sign, parentheses, x plus h plus 3, there's the end of your function. So I rewrote your function. Instead of substituting in a 3 in for x, or a 2 in for x, or a 0 in for x, we substituted x plus h in for x. Then we're going to say subtract the whole f at x, which is this whole thing. But remember, parentheses, you're not subtracting the first term, you're subtracting the whole thing. All it is a series of substitutions. That's it. Now, there's no shortcut. X plus h times x plus h gives you x squared plus 2xh plus h squared, which you then have to distribute the 4. Distribute this negative, as plus 3 stays. Distribute this negative, everybody changes the signs. I'm going to put this right under here, just for space. I'm distributing this over here. Okay, so we did it that way. Now, when it's 4 h squared, thank you. Now, when you go to eliminate, you should be eliminating anything that does not have an h. So do I have a negative 4x squared somewhere? Yes. Do I have anything else with xh's in it? No. Do I have any h squares? No. Do I have a positive x somewhere? Yes. Do I have anything else with just plain h? No. Am I plus 3? Am I minus 3? No. Whatever is left has to contain an h. Or something went wrong. You probably forgot to distribute a negative sign. Sometimes you forget to bring, my biggest thing is I forget to bring this guy down right here. I substitute in, and that's the one thing I always forget. So at the end, when my numbers don't come out, I knew I made my same mistake. I just forget to bring it down. That's a common one. So now, factor out an h. You cannot parse out terms, but you can factor out an h. And now you can take out your h. So your answer is 8x plus 4h minus 1. Your goal was to eliminate that h, because h cannot be 0. So let's just eliminate it and not have any domain restriction. Substitution. Make sure you substitute, make sure you FOIL it out, make sure you watch your negative signs. Good? Transformations. How'd your transformations look? Okay, with the transformations? You tell me, any questions with the transformations? No? On the first one, this was your reflection over your x-axis. Did it change my domain? No? But what's going to change? The range. The range will change. I didn't ask you range and domains, but know that the range changes, right? The second one also, is that going to change my domain? Yeah. This one, yeah, because it's a piece of something, right? It's not a whole endless thing. Is it going to change my range? No. Yes.
This is the negative x.
This negative x, if your x is positive and it becomes negative, where's it going? So where's the reflection? The y-axis. This negative is not next to your x, it's next to your y. So if your y goes from positive to negative, where's the reflection? X-axis. Do it with your fingers, it makes the most sense. If x is going negative to positive, your reflection's over the y-axis. If the y is going negative to positive, positive to negative, it's going over the x-axis. And these were a vertical and a horizontal you had. Remember to say vertical shift down 2 units, horizontal shift the opposite way, right 1 unit. Good? Those are not bad, right? These are kind of easier. Okay. And this last one, you had to walk me through each one of the transformations, and you have to list it in order. So pretend you're solving for x. Shoot right to that absolute value. So your core graph was your regular absolute value graph. I did it in black. Then I did the inside here. This is my horizontal shift to the right too. There's the red. As you come out of the absolute value, you're still in this term. You're multiplying by a half. There's your dilation. Because it's less than 1, it's a shrink. Greater than 1, it's a stretch. So less than 1, I'm vertically shrinking this by a factor of 1/2. It makes it slightly wider. Because you're shrinking down the distance to 0. And the last thing is the -3. So you're taking a vertical shift down 3. It's a good idea to keep track of your vertex point. You started at 0, 0. You move to the right 2, so you were 2, 0. Then you move down 3, so you're 2, -3. So if you're going to check this in your calculator, that's a good point to check. 2, -3. Okay? And the last one I told you yesterday, if it's easier, take this +5 and do it last. Because you're going to start in here anyway. You're going to go 10 units to the left off of your squaring function. That's in my red. Horizontal shift left 10. Then you're going to come out and hit that negative. That negative is not by the x, it's by the y. So it's a reflection in the x-axis. And that's the blue. And then lastly, you're going to pick this up, vertical shifted up 5. So keep track of your verticals. You moved it 10 over, -10. You moved it up 5. That'll help you do your range and your domain as well.
That negative absolute value is what
This 5 doesn't affect that negative.
but the negative made it reflect.
The negative, yeah, that made it reflect. It's a negative outside of this. It looked like this when I moved it over. That's your negative. It's closer to the y. It's not by the x, it's by the y. That's why it's easier sometimes if you move this guy back here.
Do you always want us to put the
rearrange that and then,
If I ask for it, yeah. If I ask for it. Sometimes you got enough going on with everything else that I won't, but usually I'll put the range in the domain there. Okay? And here are your operations on your functions. We started off number 11. It had a domain restriction, number 11. So there is actually no restriction in the G of X, in that function, because there's nothing you can add in the real number world. In the complex numbers, yeah, but not in the real. There's no number you can put in for X that will give me a 0 in their denominator. If you took X squared plus 1 and you set it to 0, there's your -1. This is your imaginary number. We only work with the real number set. So therefore there's no restriction in the real number. And there is nothing you can put in there that will give you a 0. So this is the only one that's giving you a restriction. And remember, this is a quadratic. So your quadratic, you find your points, your roots, you draw your quadratic, and here's your positives up here. So here's your domain right now. That's your restricted domain. That's what you're going to start with. So first time through, we're just going to add it. Yep, not pretty, but we don't have to rationalize anything. You can just leave it like that. We subtract it. Yep, not pretty. We can multiply this. Multiply this over 1. Make your life easier, and that still does not look pretty. And we can divide this. The only thing now with the divide, it says just be careful, because when you divide this, you have a complex fraction. This is a hard one. When you go to divide this, you have a complex fraction. So keep first. You change flip the bottom. And there's nothing you can do but, pull them over and multiply them across. This is the only thing that's going to change. And that's okay, because that wasn't in our domain to begin with. 0 is not part of your domain. It was negative infinity to -2 and 2 to infinity. You didn't use 0. So it didn't have an effect on your domain. These weren't pretty, but you just had to follow the rule. Is everybody okay with just following the add them, subtract them, multiply, divide them? The complex number might have been a little bit tricky. And the second one, here, this one had a domain restriction. It was in a denominator. You just couldn't use -1. So we added them. We could have left it like that. I just made it a common denominator. If you left it like that, that was fine. We subtracted them, multiply, pull it over, and divide. The divide is the one thing you can't leave as a complex fraction. And therefore, we had one additional problem in the denominator, that x cannot be 0. So you have to take that out of your domain. The divide is the only thing that's going to change your domain again, because it gives you fractions. Okay? I don't even think I made yours that hard on the test. No, you don't even have anything that hard on the test. This is the hardest you'll see over there.